Okay, let's find all the solutions of 9x is congruent to 12 modulo 15. First of all, the greatest common divisor of the 9 and modulo 15 is 3. And of course, the 3 could divide 12 at this moment. So we have solution. Not only a solution, in this case, we can expect that exactly 3 incongruent solutions. Okay, let's try to find it. First, we need to find the specific solution first, and by adding the appropriate multiples of 5. Where does it come from? Dividing this modular by the greatest common divisor of 9 and 15, okay, which is 5. Please keep this one in your mind. Okay, to find the particular solution, the one solution, we consider linear Diophantine equation, which comes from this equation. So 9x comes with this modulo my with minus is going to be same as 12. Okay, just follow me. Then using the Euclidean algorithm, we didn't cover in our course, so hopefully we have time in class to show this one, but just try to follow me. Whenever you want to solve this linear Diophantine equation, choose the equation between choose the numbers like 15 and 9 from the coefficient of x and y. Okay. Then divide this kind of larger number by smaller number. So 15 can be divided by 9 with remainder 6. Then divide this divisor with the remainder from this first equation. So divide 9 by 6. Then the remainder will be 3. And we just keep doing this until we got the remainder 0. So we need to divide 6, which is the remainder of this equation, by the quotient, divisor of this equation, and by 3, which is the remainder from that equation. So 6 is going to be 3 times 2, and finally we got the remainder 0 here. Okay, then starting from the last remainder, which is not 0, and rearrange the equation. So 3 can be written by 9 minus 6 times 1. Okay, so this first equality came from this one. Right? Then we want to get 9 and 15. That's the first two integers which are the coefficient of x and y, right, from this Diophantine equation. So until we get that on, we need to substitute each numbers, right? So in the next step, 6, we have the remainder here. Okay, then 6 can be written by 15 minus 9 times 1. So instead of 6, we substitute 15 minus 9 times 1 there. Of course, times 1 doesn't affect anything, so we don't put it. Please don't calculate it. We just want to arrange it to get 9 times something minus 15 times something, right? So 3, the last remainder, which is not 0, can be written by 9 and 15, the two coefficients of the variable. So if you multiply 4 on both sides, why 4? Because in this equation we need 12 by the arranging of this 9 and 15, right? So from 3 to get 12, we need to multiply 4, and that's another reason why we need this divisibility, right? Okay, that greatest common divisor should be a divisor of this constant term, so we can get that constant term by multiplication. Okay. So that's how we get the number 4 and multiply on both sides. Then this right hand side becomes 9 times 8, 2 times 4, and minus 15 times 4, and this 3 becomes 12 from 3 times 4. So we found the first solution of this equation. 9 and 4 should be x and y to get that equation. So this is our first solution. Then the complete solution, x was our number, right? Y is just necessary, but x is what you are looking for. So after you have 8 as the first one, then at this moment please keep this one in your mind. 8 is not the only integer satisfying that. Of course there are many incongruent solutions there, but from this solution itself, actually x should be is incongruent to 8. That's the meaning of it for modulo 15. So if you add 15 at there, for example 23 is another solution to satisfying this equation. And at 23, if you add 15 again, then it's 38, right? Then 38 is also another another solution for this one, right? So this one solution from this equation actually gives us infinitely many different solutions, right? So, but all the solutions, all the integers are actually congruent each other for modulo 15. So we just put them together because we know the property of all these integers. Just saying simply, it has one congruent solution, which is x is congruent to 8, right? No matter what x is, right? That should be one solution. The next one is just simply adding 5 in there. And the reason for 5 is we already have that one, right? It's dividing the modulo with the number 3 is 5, right? So we're just simply adding this number to the first solution. So the next one is 13. Of course, not only 13, all the integers having same remainder like 13 has for modulo 15. And if you add one more, 5 here, then it's going to be 18. But 18 is greater than 15, our modulo number. Then try to get the remainder of it, so it's same as 3. So simply you can say that 3 is another solution for that. Now at this moment, if you try to add another 5 here, we are going to get 8. So it's kind of repeat by that, right? So we finally realize there are 3 different incongruent solutions, right? It's going to be 3, 8, and 13. This is corollary, but it's so simple. You can understand it from previous theorem and the example. If a and m are relative prime, right, and b is any integer, then the linear congruency for that has a unique solution. Can you see that, right? No matter what, there is no way to get another incongruent solutions, right? Because these two numbers are relative prime. So when you see the forms, we already know how many incongruent solutions we are going to get by just simply checking the greatest common divisor.